my name is Daniel Stewart and I'll be presenting on behalf of Group 34. Our group members are myself, Daniel Stewart, Taylor Smith and Brayden Lauder. The purpose of the assignment was to safely design a shed within the parameters of the Australian Standards and Codes. Our design was to comply with Australian Standards and Codes AS 1170.0, AS 1170.1, AS 4055 and AS 4100. We were given the task of designing all members of the shed structure, this including columns, rafters, purlins, girts, bracings and other connections. As part of the assignment, our group was given a set of dimensions and a shed drawing we were to use. The span of the shed was 9 metres, the height of the shed was 8 metres and the overall shed length was 12 metres. Our base spacing was at 6 metres and the roof pitch was at 5 degrees. For our wind classification, our wind region was Region A and our wind terrain category was Category 2. When designing our wind speed for Part A of the assignment, we determined that our wind class was N3. For the first part of the assignment, we were to design the dead and live loads on Beam 1 and Beam 2. Our beams were to be universal beams as per the One Steel catalogue. Beam 1 was a rafter, this meaning that it had to support the dead load weight of the sheeting, purlins, ceiling, insulation and services. The roof sheeting we were to use was Colorbond trim deck. Its weight was 4.93 kilos per metre squared. We then had to find the weight of the purlins. In order to determine what purlins we were going to use, we had to design them. Our purlins were to be designed using the Lysart catalogue. As discussed, the roof sheeting would be Lysart trim deck as well. We then determined that the purlin spacing would be at 1.63 metres. We then did a calculation for the purlin's dead load, the purlin's imposed load and the purlin's wind load. From this, we were able to determine what purlins we would use. We decided to use a Z purlin as shown in these Lysart tables. The purlin we had selected based on our calculations was a Z330. Now that we knew what purlin we were using, we were able to go back and start designing Beam 1. The weight of the Z330 purlin was 12.76 kilos per metre. The ceiling material was to be 10mm thick plasterboard, which weighed 0.09 kilonewtons per metre squared. We then had to allow for the roofing insulation, which weighed 0.5 kilos per metre squared. We also made an allowance of 0.1 kilonewtons per metre squared for the surfaces. Our self-weight assumption was 100 kilos per metre. From this, we were able to determine the dead load of Beam 1. The dead load was 3.02 kilonewtons per metre. We then went on to design the live load and wind load of Beam 1. We then went on to design our strength combinations for Beam B1 as per AS 1170.0. In this graph here, our inward moment capacity is shown in red. Our outward moment capacity is also shown in blue. Due to an overwhelming difference in moment capacity, a decision was made to select Universal Beam 410UB53.7. From here, we then calculated the serviceability limit, which was found to be safe for this beam that we had selected. From here, we then went on to design Beam 2. The dead load calculation included Colorbond trim deck at 24 kilonewtons per metres cubed, with also the self-weight at 100 kilos per metre. The overall dead load on the beam was 22.6 kilonewtons per metre. Our live load calculation was for workrooms light industrial. This equaled to 3 kilonewtons per metre squared. This gave us a live load of 18 kilonewtons per metre. We were then able to do our strength combinations for Beam 2. As marked in red on this graph, we selected Universal Beam 360 UB 50.7. We then calculated the serviceability limit for this beam, which showed that it was safe to use. From here, we went on to column design. For the next part of the assignment, we were to design column C1. We first started by determining the dead and live load on this column. The column was to be a universal column. The column was to take the weight of the first floor, which was a 150mm concrete slab, the rafter beam 410 UB 53.7 and the floor beam 360 UB 50.7. The column height was at 4 metres tall. From here, we were able to make an assumption of what we thought the column would be. This assumption was a 150 UC 37.2. We were then able to make assumptions and determine the live load on the column. From here we could do the load combinations and then determine the buckling on the universal column. As shown on this table by the Australian Steel Institution, the column that we had selected, 150 UC 37.2, was found to be suitable for our design. If we wanted something more economical though, we could have referred to a 150 UC 30, as this would have also been suitable. We then went on to our girt design, finding the girt's dead load, win load, and using Perlin design to determine the member size. Using the Lysart table, we decided on a Z girt. The girt we had selected was a Z25024. Now that we had determined all the sizing for all the members, we could input this information into SpaceGas. We then entered our shed design into a program called SpaceGas. The dead and live loads were then applied to beams B1 and B2, as well as column 1. This then gives us a model in which we can analyse the data for bending moment, shear force, deflection of beam 1 and beam 2, as well as the actual forces in column 1. This screenshot shows the dead loads applied to the model, as well as the bending moment, axial forces, the displacement, and also the shear force for dead load case models. We then have the live load case models, live load axial force, bending moment, displacement, and shear force. To simplify it, the group has put these figures into a table, although these figures cannot be directly compared to the manual calculations, since the manual calculations consider the maximum value obtained from load combinations. Therefore, the load calculation used for each member must be implemented into the SpaceGas model. This is so we can see whether or not our manual calculations were correct. The new load calculations were then put into the model, and these were our results. It was found that with the SpaceGas data that we got given, our manual calculations were correct. This proves that the beams and the columns that we had designed and selected through the manual process are more than sufficient to support the shed structure. Thank you for watching, and I hope you enjoyed this presentation.